Welcome to Ask and Learn.
In this problem, we have saturated water vapor, which is contained in a spring-loaded piston cylinder device and is condensed until it is a saturated liquid at a specified temperature. We need to calculate the heat transfer in the process. We assume that the cylinder is stationary and thus the kinetic and potential energy changes are zero. There are no work interactions other than the boundary work. The thermal energy stored in the cylinder itself is negligible, and the compression or expansion process is quasi-equilibrium. Now, before we get to the PV diagram, we can write the energy balance of this equation, since the system is closed, as E in minus E out is delta E for the system, the change in energy. Now, the energy into the system is due to the boundary work, since this is a condensation, and the energy out of the system is due to heat. So W in minus Q out is equal to the change in internal energy of the system, delta U. And delta U can be written as M times the specific change in internal energy, little u2 minus little u1. So we can write this as the heat transfer out of the system. We rearrange this equation is the boundary work into the system minus M into the change in internal energy, u2 minus u1. So if you divide both sides by M, we get the specific heat transfer Q out is equal to the specific boundary work minus u2 minus u1. So that's our energy balance equation. Now, the properties of our initial and final states are as follows. So P1 is equal to the saturated vapor pressure at 200 degrees Celsius, and that's 1,555 kilopascals. And so we'll do state 1 first. So the specific volume at this state, V1, is equal to Vg is 0.1272 cubic meters per kg. The specific internal energy for state 1, U1, is Ug at 200 degrees Celsius, which is 2,594.2 kilojoules per kg. Now for state 2, our pressure P2 is the saturated liquid temperature at 50 degrees Celsius. So this is 12.35 kilopascals. Specific volume V2 is equal to Vf at 50 degrees Celsius, which is 0.001012 cubic meters per kg. The internal energy of state 2 is Uf at 50 degrees Celsius, which is 209.33 kilojoules per kg. So from our tables, we found our properties of the initial and final states. Now, if we go back to our PV diagram, we can see that the initial pressure P1 is 1,555, and that's in kilopascals, and the final pressure is 12.35 kilopascals. So our initial pressure is higher than our final pressure. Now, since this is a linear process, we can calculate the work done in this process, and the work done, or the specific work done, little w, out of the system, the boundary work, is the area under the PV graph. So the area under our process line 1, 2 gives us the boundary work of that process. So we need to calculate the area of the shaded region. And that's the area of the trapezoid, which is P1 plus P2 over 2 And we're using specific volumes here. So that's little v2 minus little v1. And these values are all known, so we can substitute them in. So this is 1,555 kilopascals plus 12.35 over 2, we'll suppress the units here, into V2 0.001012 minus V1 0.1272, that's cubic meters per kg, and we get the boundary work out to be minus 98.9 kilojoules per kg, which simply means that the specific boundary work into the system is equal to the minus of that value. So it's 98. The net boundary work is into the system, so that's 98.9 kilojoules per kg. Now that we have the specific boundary work into the system, we can substitute this into the energy balance equation and find the specific heat transfer. So going back to the energy balance equation, we have the heat transfer, Q out, the unit mass is the boundary work into the system minus the change in internal energy, U2 minus U1. And so this is 98.9 kilojoule per kg minus U2, which is 209.33 minus U1, 2594.2 kilojoules per kg. And so we get the heat transfer in this process to be 2,484 kilojoules per kg.